Hello, my name is Steve Hencher. I'm Professor of Engineering Geology at the University of Leeds. In 1990, I was local secretary for a conference on weak rocks by the Geological Society of London. Most of the presentations were published in a volume produced by Balkema in 1993, but there's one exception. The paper that's missing is by Everett Hook, who was then professor at the University of Toronto. Now, recently, I found an audio tape of that lecture and contacted Everett and asked him whether he was interested in having it put online, and he was quite enthusiastic and has sent most of his original slides. So the lecture is significant in that it sets out his philosophy over rock mass strength and rock mass deformation. And in answer to a question from John Sharp at the end, he presents reluctantly one of the early versions of the GSI, the Geological Strength Index. So it's a significant lecture. Anyway, you will hear various voices. Most of them we've managed to identify on a photograph of the proceedings. A couple we haven't, and apologies for that. Maybe somebody can contact us and tell us who they are, and we can identify them. Anyway, listen and enjoy.
At least show some sign of recognition this morning. We're back now into the second of our themes, weak rock masses, we will be discussing today. And to present the keynote lecture on that subject, we're delighted to have Professor Everett Hook from the University of Toronto, where he's research professor in rock mechanics. Now, he really needs no introduction. Those of you who are my age and slightly less will know all about him from the heyday of rock mechanics in UK when he was at Imperial College. And I suspect those of you who are a lot younger will still be using his books in the course of your normal work. So without any more time wasting from me, I'll ask Everett Hook to present the keynote address.
Thank you very much, Mark. Yep. Good morning to you all. On Monday, I attended some of the session and found that most of the discussion assumed that weak rock was weak intact material of the kind that I've illustrated here, a very weakly cemented limestone from a project in Tunisia. And indeed, some weak rocks are of this type and present real engineering problems. This is a dam site in Tunisia where that particular very weakly cemented limestone existed, and it had problems of its own. Materials with high active clay minerals, I would say, fall into this class of weak rocks or strong soils, and they have problems all of their own as well. So that this little road to a quarry site in Colombia, you see even the slopes of 2 or 3 meters higher in the state of, or in a state of failure. There's a tunnel in India mining through a fault of about several hundred meters wide of very poor gouge material, and the only way that progress could be made here was by a technique of spiling, where what you have is a steel set. You drive ahead just with a big hammer, steel pins, which form an umbrella over the face, and you mine the face half a meter at a time, put in the next seal set and progress that way at several meters per year rate of phase advance. That's not really the kind of material I'm going to talk about today. Most of my experience is in the hard rock field, and weak rocks, to me, are those rocks which fail when subjected to the stress conditions of the environment in which you're working. I've just completed a paper with Don Moy, and the first paragraph of that reads, in the context of this chapter, weak rock is rock which will fail when subjected to the stress levels induced by the excavation of large underground caverns at depths of 100 to 300 meters below surface. Sedimentary rocks such as bedded sandstones, shales, siltstones, and mudstones are amongst the rocks which fall into this category. It's a paper on large underground powerhouse cavern design. But basically what I'm saying is that irrespective of what the intact rock is, if that rock will fail when subjected to the stress conditions of the environment, then as far as I'm concerned, it's a weak rock. And to take a ridiculous example, I'm currently working on a 33-meter diameter spherical cavern at a depth of more than 2 kilometers in the Canadian Shield. And although the rock mass strength might be in excess of 150 megapascals, it will fail under those stress conditions. Now I'm not dealing with that end of the spectrum, but I'd like to pick up a comment made, I think, by Brian Hawkins on Monday, that we shouldn't forget the discontinuities. And it's those discontinuities, the joints, faults, fissures, bedding planes, that make rocks which are otherwise good rocks weak from an engineering point of view. In this slide, I've tried to illustrate the progression from intact rock, which could be the weakly cemented material that we've just seen, or it could be very hard igneous or metamorphic type rock, and the introduction of geological discontinuities, or in some cases, discontinuities induced by blast damage, renders that rock weak. Now, we have to progress through a fairly systematic introduction of first one and then two and then several joint sets. And the behavior of rocks in this category here are really anything but simple. They're highly anisotropic in their behavior and don't fall within the scope of this topic today. But when we get down to the situation here where we might have 6 or 7 closely spaced joint sets, then when you're dealing with a large structure such as a slope or a big tunnel, for all practical purposes, that rock might behave as an isotropic, homogeneous, but very weak mass. And it's that type of rock mass that I want to talk about today. Starting at the very hard end, this is a granite in Zimbabwe, and the type of core that you would obtain from that material would be something like this. In fact, many of those core sticks have to be broken to get into the box. And clearly you're working in an ideal material here. The type of tunnel you might be able to excavate is illustrated here. And this is certainly not in the category of a weak rock at all. But the introduction of one or more discontinuities leads us to the problems of stability in both slopes and underground or foundations that we have to deal with. A few discontinuities in relation to the size of the opening will result in structurally controlled wedges or blocks which fall from the surface of the excavation. But as the intensity, the number, and spacing of joints, to use joints as a generic term, increases, so one gets much more into the situation where the rock will fail almost as a homogeneous material with quite different properties from the intact rock. In fact, what I'd like to do is to run simultaneously here an overhead, which is a slide from Nick Barton. And I've given the reference to it, if you can read it, right at the bottom there. It was published in a conference in Hong Kong last year. And in that slide, which I'll leave up while I go through these, he's plotted here his rock mass quality, which is a tunneling index that I'm sure many of you are familiar with. And it's interesting that that index does not contain any reference to the strength of the intact material. It's really based entirely on the level of the number of joints, the condition of the joints, and the degree of alteration. And if we work down from the very hard end, which you've just seen here, down towards the exceptionally poor end, many of the rocks with which we are concerned fall in the category, I would say, from very poor to fair or good in this area here. So I'll leave that on the board as I go through these slides. This would be at the very good end, but you would have to deal with problems like this by limit equilibrium analysis. This is a typical wedge failure in a slope where you have, as you see there, two intersecting discontinuities with sliding along either one of those discontinuities or along the line of intersection. And the properties of the intact material really don't come into it. You're concerned here with three-dimensional geometry and with the shear strength on those two surfaces. So this is not in the category of weak rocks at all, but I'm just passing through this series as we work towards the weak rock end. Similarly, in the tunnel, you have intersecting discontinuities giving you this type of sidewall failure. As we add more and more discontinuities, here's a gneiss in Sri Lanka with very nice orthogonal jointing and a few weak features running through it. We tend to work more and more towards the isotropic homogeneous end of the spectrum, and in a slope like that, we might expect to see core of this type, where you still see substantial intact rock pieces, clean discontinuities, very little rounding of the particles in the core box. A little bit worse, closely spaced and more of them, discontinuities, and we're now starting to get to the point where, on the scale of a very large slope, if you were talking of a slope or several hundred meters high or a very large cavern, you might be tempted to look at this rock mass as a weak homogeneous isotropic system with very special properties. And the determination of those properties is something we'll talk about a little bit later on. So we'd now be talking for this rock mass of something I would guess in the fair category on Barton's classification. I don't know the equivalent. Well, it would be pretty similar in Beniowski's classification as well, pretty similar category. And we'd expect to see a lot more disturbance in the core here. By the way, can you see that slide with the overhead on? Yes. It's not bothering you too much. Okay. So what we're seeing here is fairly close spacing of discontinuities in the core, some disturbance of the core, perhaps some alteration on the surfaces as well, particularly if it's near surface and you've had weathering penetrating down into the rock mass. And yet, worse yet again, in an underground opening, this time with a lot of weak discontinuities, a pile of rock lying on the floor there. And in this kind of situation, you'd expect to see much, much more disturbance in the core. The core pieces are still pretty much intact. There's relatively little rounding except for a bit up at the top there where you see sort of gravel-type particles. And the interlocking of these particles plays a key role in the behavior of that rock mass. I'll talk about that in a moment. So now we've moved down to perhaps the poor to very poor category, and we've moved through the spectrum to a situation where we're dealing with heavily jointed, weak rock masses of this kind. Now, there are other factors that can also influence the behavior of the rock mass in addition to simply the discontinuities. So far, I've assumed that you have a reasonably good rock which is made discontinuous by a large number of joints or bedding planes or whatever. But in addition to that, you have weathering or tectonic disturbance of some kind, which takes us into the extremely poor category. Here's a slide from cutting in Taiwan, and you'll see the rock has been fairly heavily chewed up by tectonic activity. It's very difficult. You can see the remnants of a structure there. You can see bands of fairly hard sandstone in there. But on the whole, that's been fairly deeply weathered and mashed around to the point where it really has no residual directional property on a large scale. Here's some core stones from weathering, again in Taiwan. And you can see that although you might have fairly strong pieces of sandstone here, the surrounding material has been very deeply weathered and in many cases down to a residual soil. Slaking is another problem where on exposure some of the shales will slake like this, and that renders them, at least near surface, weak rocks. And in general, that presents a slightly different problem from the problem of an overall weakness in the rock mass. This is a surface effect, and it's generally dealt with by shotcreting or some type of surface protection. A case in point, these are cores from a project in South Africa, the Drakensberg project, and there are a couple of people in the audience who worked on this. And this is fresh core straight out of the borehole, and this is similar core about 6 months later, so that the mudstones have disintegrated completely. Some of the siltstones are still partly intact, and the sandstones, the outer two cores, are still in pretty good shape. Now, in that case, because this was a result of weathering, the technique that was used was to shotcrete all surfaces immediately on exposure. And so right at the face, the shotcrete was applied, and then another layer applied later on for final treatment of this cavern roof. That's a 17-meter span cavern in that type of material. Now, how about the mechanics of failure of these types of materials? Let's go back for a moment to assume that we're talking about a fairly good intact material which has been rendered discontinuous by a number of joints. In this case, only two. This is an experiment carried out by Ladagna and Archambault at the École Polytechnique in Montreal. And what they did was to cut little concrete prisms and build a very large model, several meters in size, and tested it biaxially. And what you see here is the typical type of shear plane which you might anticipate, but which involves, in this case, actually fracturing through the intact material. So the little blocks, which are located vertically and horizontally in this case, are failed through because the stress field doesn't really see those discontinuities. It's parallel to the stresses. But as you start inclining the discontinuities, this is about 20 degrees, you'll see that we've lost a distinct shear surface, and we're now into a zone of mashed up material. You've got some rotation starting to take place, some crushing of the particles. And if we progress to the 45-degree orientation, you'll see quite a different pattern has developed. In this case, there's virtually no failure of the intact material, but there is a good deal of rotation, and if you follow one of these layers down, you can see that you get a kink band forming. So that this material goes through a deformation mechanism which does not involve failure of the intact materials at all. And this mobility of the jointed rock mass is a critical factor in its engineering behavior. It's something that has become evident to us as we've progressed with work on jointed rock masses, that you really have to consider almost two categories. In the one extreme, you could talk about a rock fill, which is a transported material it could be exactly the same block size, particle shape as this, but it has been transported, and therefore the blocks no longer fit perfectly together. That would be the lower end of the spectrum. The upper end of the spectrum would be an in situ fractured material which has not been allowed to deform, and the strength is quite different between those two ends of the spectrum. One of the most elegant experiments that was ever carried out was done by Rosengren and Jaeger in Australia many years ago. And what they did was to take marble specimens, heat them, first of all prepare them for triaxial testing, heat them to about 600 degrees centigrade, at which temperature the differences in thermal expansion break the bonds between the particles completely. So you have little particles of marble completely separated from each other with the cement bonds are completely broken. So you have a perfectly interlocking, low porosity, zero tensile strength material, the ideal weak rock mass. And you'll see that you have very little reduction from the intact strength of the marble, which I've plotted there as a more failure on rope. It's highly curvilinear in nature. That's the blue highlighted line. And the granulated marble, which has zero tensile strength. In fact, this curve really should come down much more sharply here. So it has zero effective cohesion and zero tensile strength. So the granulated marble has, apart from that end, dropped very little in strength because it is perfectly interlocked. You can induce this artificially in the field by blasting. Here's an example from Argentina, where on the left-hand side you have a face that's been created by pre-split blasting, which is probably the most gentle form of mass blasting that we can employ. And on the right is a typical mass blast. And you'll see that the particles on the right, particularly those near surface, have been dislodged. The integrity of that whole system has been broken up by blasting. So the difference between an interlocking strong rock mass and a weak mobile rock mass could be that there has been movement, tectonic or stress relief movement, or you could have just blasted the hell out of it and rendered it weak by your own making. An example of these two extremes, again, I illustrate with this mine, Bougainville in Papua New Guinea. This is an old photograph. The mine is now, it's not operating at the moment because of some internal problems in Papua New Guinea, but it will eventually have a cut height on this side of 1,000 meters. The rock mass is very, very strong granodiorite, 256 megapascal strength, but as you see, very heavily jointed. The longest piece of core I ever saw in the early exploration days was about 1.5 inches. And so when you're talking about 1,000-meter high slope with core like that, we decided in our wisdom to treat it as a special kind of soil. And most of the early analysis used a simple Bishop circular failure analysis. You'll see that on a bench scale there is some relic structure. You can see some of the discontinuity sets do in fact form wedges. But if you leave a bench to stand, it just falls apart over a period of several weeks. Now, the attempts to control the blasting there were very serious over a long period of time, and they found that because of there are probably 7 or 8 joint sets in that rock mass. There are enough discontinuities that the blast gases just vent into these and destroy the rock for up to 150 meters or so behind the last row of blast holes. And just a practical note, when you're blasting in the scale of Bougainville, they move about 200,000 tons of rock a day, and each blast is about 75 tons of explosives. So it's very, very difficult to control that size of blast, to make it very gentle. So eventually they decided to stop the blasts short of the face and to rip and doze. So the blasts are now stopped. When you're approaching a final face, the blasts are now stopped about 19 meters from the final crest line. That rock is still damaged, but only marginally so. And then D10 dozers move in and basically rip and doze the final face, so that what you end up with is that sort of face. Stands at 55 degrees, and that's controlled by the jointing in the rock mass. You can literally go and mine that by hand. You can go and pick out pieces quite easily. But as you see, with a very gentle process there of dozing, you've left the rock mass intact, or rather interlocking, and largely undisturbed. And all of the final faces on Bougainville will eventually be done by ripping and dozing. This is a trial section that you see back here. The benches will be triple bench, so they'll be 45 meters high, cut by D10 dozers. And the essence of that little story is that what they've tried to do is to leave the rock mass as undisturbed as possible, to keep it interlocked, to keep the little pieces tightly together. This is dry work. How do we test these types of rock? Well, this is a major problem, because in general you're talking about rocks which might have strengths from 50 to 250 megapascals intact strength. Although that strength might drop by a factor of as much as 100, you would still be faced with uniaxial strengths of, let's say, 2 to 10 megapascals. And to test that on a realistic scale, you would have to talk about blocks of several meters in dimensions. And it really is extremely difficult to do this. In the early days of Bougainville, attempts were made to test the rock in rock fill cells. This is a 22.5-inch diameter, 46-inch long specimen-sized cell in the Snowy Mountains Laboratory in Cooma in Australia. This is the cell back here. And samples were gathered at Bougainville, shipped down to Cooma in 44-gallon drums, poured into the cell, lightly recompacted and tested. But from what I've just said, you'll realize that this rock was completely disturbed. It had been transported, and no way in the world could you put together that interlocking matrix that existed in the original slope. Nevertheless, it was as we moved on in the understanding of that rock mass behavior, what we tried to do was to take grab samples from the faces, consolidate them under uniaxial loading to as close to the in situ density as we could, check the grading curves to see that we hadn't destroyed too many particles, and test these in a 6-inch diameter triaxial cell on the mine itself. And here's the sleeve ready for loading, and this is the 6-inch cell that was used there. That gave pretty good results, but not as good as results which were obtained by triple core drilling some of this material at 6-inch diameter cores, transporting it back to Canberra inside the inner tube, and tests were done by Professor John Jager at Canberra, where the inner tube was split, a copper sheath was wrapped over the core, and it was very gently transferred into a triaxial cell. So those specimens were as close to any I know, other than Rosinger and Jager's tests on granulated marble, were close as any I know to undisturbed jointed rock masses. The geotechnical program on Bougainville cost well in excess of $1 million. the capital cost of the mine in 1970 dollars was 400 million, so it would be well up into the billions now. And clearly, there are very few projects that can sustain $1 million geotechnical program. And out of that total program, we had maybe 20 test results. And those 20 test results comprise about 80% of the world total of good test data on jointed rock masses, at least that I'm aware of. So it's a very difficult subject in which to get real hard data to work with. There have been a few other tests done, but very, very few in nature. So it's a major challenge to the geotechnical community. How do you actually test jointed rock masses, which are weak from an engineering point of view, on this kind of scale? It's a huge problem. You can do some in situ testing, and this is on a small project in Taiwan, plate bearing tests to determine the modulus of deformation. These work reasonably well if the rock mass modulus is, I would say, less than about 10 gigapascals. I'm just going to change this over. But for harder rocks, they really don't work with a dam because you can't get enough steam into the equipment and you can't measure the deformations accurately enough. So I actually prefer to use this graph. It's a lot cheaper. And in general, it turns out to be adequate for most applications. One of the things that I would bring to your attention is it's really necessary when you're contemplating what tests you need to do, what site investigation you need to do in this kind of rock mass, is ask yourself, first of all, what difference does it make? And it's usually very beneficial to do a lot of sensitivity studies. Let's say that you're involved in designing a gravity dam, concrete gravity dam, and you're looking at the foundation modulus. Run through a series of studies and see whether it makes any difference. And very often it doesn't. Very often you could go from say 10 to 25 megapascals and not see any change at all in the stresses in the dam or the overall stability of the foundation. So I think you really have to ask yourself when you are contemplating these horrendously expensive tests, how accurately do I need the results and do I really need to do this? And I find personally that little chart by Seraphim and Pereira, RMR there, by the way, refers to Beniowski's rock mass rating. And I find that is adequate for many of the foundation or cavern type studies in which I'm involved. Obviously, if you find from your sensitivity studies that you do have a problem, then indeed you may have to contemplate tests of this kind. But be aware that they extend only over a relatively limited range of deformation moduli, because once you get above, well, let's say 40, certainly, you'd find that you simply couldn't measure it, because you can't measure the deformations and you can't get enough load into your equipment to do that. I'd like to, I'm just going to switch this off now. I'd like to suggest another technique, and I was encouraged recently to find a Japanese paper. Unfortunately, I don't have it with me, so I can't give you the reference, in which it was suggested that one of the best ways of studying the behavior of weak rock masses might be the back analysis of deformations of large-scale openings. That's a fairly obvious statement, but this guy has actually laid out some methodology where one might be able to do this. And this is an example from Taiwan, the Mingtan pump storage project, which is located in the geographical center of Taiwan. It's a 25-meter diameter span cavern in interbedded sandstones, siltstones, mudstones, shales. There are 21 faults running through the cavern area, so it's a weak rock mass. And this is a typical surface outcrop on the site. The hard pieces you see there are the sandstones, and the rest you can use your imagination on. Not a great rock mass to build a cavern in. In underground exposures, this isn't one of the exploration adits, and you see occasionally thick layers of the strong sandstone interbedded. In this case, there's a bedding shear there, several centimeters thick, interbedded with siltstones and mudstones and a whole sandwich of garbage. The many analyses were carried out on this project, including ongoing nonlinear analysis as the cavern excavation progressed. But in the context of this discussion, what was important was that we were able to get in from this drainage gallery, which is 10 meters above the cavern crown, long before the main excavation started. That was carried out during a preliminary contract. Reinforcement was placed there, but more importantly, extensometers were placed from that location along the cavern crown before excavation started. So we had very close to a zero reading on those extensometers. As the cavern was excavated from a top heading, slashed out, and then benched downwards, continuous monitoring was carried out, and the results were reanalyzed throughout the program. That process has not yet been completed, but the early indications I'm going to use here to illustrate what one might do in terms of back analysis of jointed rock mass behavior. Now, this is on a real scale. You're talking here of tens of cubic meters of rock. The distance between those two excavations there is 10 meters. This is the central top heading that's used to start off the excavation. And there were extensometer points at these distances here, 1, 4, 7, and 9 meters from the measuring head up here. And the measured dots here are measured displacements. 30 millimeters, you see, is the measurement at that point there. Now, in order to fit those measurements to the rock mass properties, it was found that a halo of about 2.5 meters had to be put around the excavation. This represents partly blast damage material, but partly material which has been rendered weaker by relaxation. As the excavation is created, it relaxes inwards. And you'll see that the properties are quite different for these two materials. This is a progressive failure type analysis using a finite difference method. And you'll see that here we have a modulus of 60,000 kilograms per square centimeter. Forgive the units, but you work in the units of the local currency, as it were. And this is in Taiwan. Cohesion of 10 kilograms per square centimeter. Friction angle of 50 degrees. Friction angle of 50 degrees might alarm some of you from the soil mechanics field, but it's not at all uncommon where you have these very strong interlocking rocks and you're working at very low stress levels, so that the curve, which is the failure curve, is highly curvilinear and in fact comes down to a 90-degree friction angle at zero tensile strength in a truly broken material. So 50 degrees cohesion of 10 for the, should I say, undisturbed material, and in the immediate vicinity of the top heading, a third of the modulus, 20,000 kilograms per square centimeter, the cohesion drops to 3, the friction angle to 40. And as I say, it may be that this represents one of our best techniques for analyzing the strength of jointed rock masses once we have adequate numerical tools to do the job properly. I'm not convinced that our current numerical tools do that, by the way, and that could be the subject of another week's discussion. But we're getting there. The tools are getting better. And as I say, I was encouraged to see a recent Japanese paper where a methodology for doing this was laid out. And we will see over the course of time whether we can add to our sum total of knowledge, which is not fantastic, as you can gather, on the behavior of jointed rock masses. That cavern, by the way, is now complete. This was in the early days, and in spite of our best efforts, you see the blasting isn't fantastic. You can see the dipping structure of the bedded sandstones here, giving you a fairly ratty roof. But as you move away from that, as the excavation grows larger, and there's a good layer of shotcrete on there now, that becomes less and less significant. And finally, when the cavern is complete, and it still had a bit to go when this shot was taken, you end up with a pretty good-looking cavern that's 25 meters span, 46 meters high, and in spite of the rock mass being of a poor quality, it's still manageable provided one treats it with tender loving care from the first to the last stage of excavation. Well, I could go on, but I'm not going to. Because you were late with your buses, I speeded things up, and I've speeded them up to the extent that we still have 15 minutes left. So, in fact, I'm going to quit right there, Brian. I'd be happy to answer any questions. Yeah.
Okay, Tony Biddle, Billington Osborne Moss Engineering. Can you tell me the diameter of the cores that you used in order to get an appreciation of the overall strength of this rock mass that you were talking about as being the most successful method?
Yes, there are several things. The tests that were done in Australia by Jaeger were 6-inch diameter triple tube cores. So they were drilled from the sidewall of an adit, in fact, 6-inch diameter. But in general, it's very difficult to justify going bigger than NX, which is about 2 and 3/4 or so. For most engineering projects, you have to make special provision for large core drilling. There are cases where you might go to Calyx, which is 1 meter diameter, but you can only use that in very shallow dam foundation type studies. In general, we work with NX size of cores, that range of cores, because in real engineering terms, that's about what you can justify.
Arinos Tavares from Brazil. My question, Dr. Robert, just answered. You showed here that you have been using triaxial tests in order to determine the shearing strength of the rock material. And my question is in the direction of the economy. You don't think so that if you use direct tests, it will be less expensive to evaluate the shear strength of this type of rock?
Yes, what you're saying is, should we not do direct in situ shear tests or triaxial tests? And indeed, many proposals have been considered for that. On Bougainville, I remember we talked about building a big shear box which we could drag behind a D10 Caterpillar and perhaps put something on top of it to form the normal stress. But it turned out not to be practical. And I would say if you can devise for the critical areas on your project where you need to do the test, if you can devise a reasonable in situ test where you think you're going to get enough load, enough displacement, enough control, then it may well be cheaper. But another subject altogether, which I haven't really touched on today, is there are methods where I think you can use these classifications to estimate the rock mass properties to an adequate degree to an adequate level that at least you can do all of your preliminary studies. And again, I say with Professor Oliveira that you really have to define your problem very precisely before you embark on either triaxial testing in the laboratory or in situ testing, which I would think may be even more expensive.
I think so. Okay. Thank you.
John Hudson, Imperial College. You showed these graphs of the RMR, and you do some calculation like -10 and divide by 40, and the RMR is composed of 5 attributes of the rock. Now, I'm always amazed that works at all, that you take these 5 attributes and they're somewhat subjective perhaps in measuring them. And there's a paper later on this afternoon where there's different functions of the RMR for the modulus. Now, the question is really, are you surprised by the fact that you can perform these manipulations on the RMR, which is very empirical and not arbitrary, but you have these classes and so on. Yeah. Now, why is that? Is it because everything comes out in the wash with these discontinuities and you get a good answer, or did you have a sort of feeling for why it works at all?
Yeah, I think that's a very good question, John. And I've just run a short course here, and it came up, exactly the same point came up in discussion during the course, because that equation does not contain any reference to the intact modulus. And then the question is, how can you calculate a modulus when you don't have a starting point? We have recently at the University of Toronto been looking at what makes jointed rock masses tick. And it seems to us that the critical components are the block size and shape, assuming that you have enough of them, the block size and shape, and the condition of the discontinuities, whether they're shared or clean and rough. And that if you think of both Benioffsky and Barton's classifications, both of which were derived for tunnel support rather than for rock mass characterization, and so they contain redundant terms like groundwater, which we exclude from our use of them. Nevertheless, in the graph that I showed there, when I was talking about rock mass strength, there's no intact strength included in Barton's classification, nor is there a modulus included in Seraphim and Pereira's chart. And I think the answer is that it does come out in the wash. I think that in general, what that means is the types of rock with which you are dealing would have intact moduli within a particular range, and if you're talking about strength, would have a intact strength within a particular range. And that is totally, although it's there in the sort of in the guts of the equation, it's swamped by the discontinuities, their orientation, their degree of interlocking, and the condition of the joints. And I've recently had an MSc student look at that equation, and we've gone back and plotted modulus ratios, and you get scatter all over the map. It really doesn't work as well as the simple relationship that was shown on that graph. So I don't have a terribly precise scientific answer, but to use your words, it comes out in the wash. And in the end, that's what matters.
Mike DeFreitas, Imperial College. I wonder whether Professor Hook could say something about the role of water in these materials. Quite a lot of the excavations you go into in reasonable rock that is relaxed exhibit quite clean joint faces, which are now iron stained. In other words, the rock mass, which was once an aquiclude, if you want to think of it in those terms, didn't have any water travelling through it, is now connected with something that has got water, and the thing is containing water. What does one do with calculations when this thing is likely to occur, and what sort of instrumentation would you recommend under these circumstances?
Thank you. Again, a good question. Water, I think, has many roles in the behavior of jointed rock masses. I was just a few days ago underground in some small mines in Zimbabwe, and they've had several years of dry weather now, and so you can go into areas where there are gouge zones which have dried out completely and desiccated, and if you tested them as soils now, you'd have friction angles of maybe 20 degrees, and they are dry, desiccated materials. But the next heavy rain, all hell is going to break loose, because those are going to revert to weak clays, saturated clays, and with friction angles of maybe 11 degrees or something like that. So the if you like, the chemical action of water, I think, as a weathering agent, as an additive to materials that react badly in the presence of water, is important. But in general, in weak rock masses of the type that I've been talking about, where that is not generally the case, where you have maybe stained, but where the properties of the surfaces do not alter materially with wetting, then I really tend to treat it as a pore pressure problem, as an effective stress problem, so that stability analyses, both underground and surface, would look at it as a simple effective stress problem. You'd look at piezometers as your instrumentation. You'd look at drainage and grouting as your water control measures to try and deal with that in much the same way as you would in any other rock mass.
John Sharp from Geoengineering. I know Everett well enough, so perhaps you'll forgive the question, but since he's involved in research, and some of us have to sort out practical solutions on an everyday basis, it is this question of the strength of rock masses, I think, that is of great fascination. We've touched on the question of looking at deformability estimates from things like RMR, etc. But really, when we come to strength, particularly of a constrained rock mass, to be used in an underground sense, then I think we're an order of magnitude into more difficult problems. And really, it was just to have the opportunity of asking Everett how he sees things going. He spent many years sort of looking at this problem, but hearing today perhaps the reincarnation of testing techniques that were around 30 years ago, where we take a sample to a laboratory, we change its stress state, we test it under a completely abnormal stress state, and looking at the realism of today's rock mechanics, where we realize that stress state, stress path, etc. are so important. How does Everett ever see us getting into the rock as it actually behaves in situ? And I know it's a subject of another lecture and it's an unfair question, but perhaps a few comments.
Well, it is, John, a long topic. In terms of the response to stress paths and so on, I really cannot conceive of a better method than the back analysis of the full-scale structures. Probably the simplest being dam foundations, because there we have a fairly well-controlled load, the impoundment water, and incidentally, a lot of those points on Serafim Pereira's graph come from back analysis of dam foundation deformations. And I think one has to try and think on the scale of the problem at hand. So this is why although I've mentioned testing, and Professor Oliveira has said the same, you really have to be very, very careful that you test at an appropriate scale. And in many cases, it's just not feasible to do that. You just cannot get your hands on a big enough piece of rock to do that. So I have spent a lot of my last 20 years looking at ways of trying to estimate rock mass strengths, and I wasn't going to show this, but since you've pushed me towards it, this table, which horrifies me, is one of the few around that I'm aware of that actually attempts to relate rock mass properties, in this case two constants m and s, which are rather like c and phi. They're nonlinear, but their m is equivalent to phi or tan phi, and s is equivalent to c. And what I've tried to do is relate these to actual geological descriptions of rock masses. And over the years, as we've used this chart and as we've learned how it operates, we've had to increase the original, which was just the vertical lettering, M and S values. We've added another italicized line there, which is for the undisturbed. So we distinguish between disturbed, which would be for slopes and near surface foundations, and deep level constrained materials. And I find it embarrassing to talk about this myself, but constantly I come across people who are using this totally out of context because there isn't anything else. I wish there were. And what I see is the efforts that I'm making at the moment are trying to refine this. I'm trying to divorce it from Beniowski and Barton's classification. Much as I admire those, and I wholly endorse their use for the design of support, they were never intended for estimating rock mass properties. So I've tried to go back and evolve another classification, which David Wood, who you know is working with me on, to try and get back to the fundamental engineering geological components that make a rock mass behave the way it does. And with back analysis of real structures, we're trying to fit together values which may not turn out to be M and S. They could be C and phi or anything else you like. But there has to be some ultimate mechanism to enable us to link real solid engineering geology observations that can be carried out simply and quickly and cheaply in the field, and at least a good estimate of how that rock mass is going to deform and fail. Because in real terms, that's the only practical tool we're going to have for most of our studies. Now, if you've got that, and this, for want of something else, is used currently for feasibility studies, for preliminary scoping studies. Once you've done that and you determine that you do have a real problem, then, as Professor Oliveira says, you either take that material out and don't waste your time testing it, or you devise a set of tests specifically to solve that problem. But there has to be some, in my view, mechanism like this, and I wish more people were working on it. I feel awfully lonely out there. I'm not a geologist. I wouldn't know geology if I tripped over it. I'm a mechanical engineer. And yet this graph has been taken and used by people because there isn't anything else. I wish there were.
Well, I think we'll have to call a halt there for the moment. I think we ought to thank Professor Hawke for giving us that opportunity of delving deeper into his wealth of experience.